So section 5.4, we're talking about differentiation and integration of the exponential function. So it's a little bit different in terms of the way the sections have been broken up so far, because typically we're talking about either differentiation or integration. Here we're going to talk about both, but very quickly you'll see why mathematicians love E and ln. One of the reasons we love it is because it's really easy to differentiate. So the first page and a half is kind of a Algebra 2 / pre-cal review. So it's just kind of a refresher in terms of, e to the x is the inverse of natural log of x. How we, just maybe one example here of how to solve an exponential equation, and then kind of an example here of how we can solve a logarithmic equation. So you should look those over and make sure you understand those before you move on, because we're going to use some of those properties and those strategies later on as we move through some of these differentiation and integration problems as well. The next page again starts off with some review, just talking about the exponential function and its properties. We have natural log of x here, and its inverse, of course, is a reflection across the line y equals x. So here's y equals x, and here are some of the properties of it. Again, really just some review of what we're dealing with here in terms of e to the x, but you can see it there. All right, so let's talk about taking the derivative of e to the x, and here is why calculus students and calculus teachers love exponential functions. Look at what the derivative of e to the x is. Oh, that's sweet, isn't it? Nice. Okay, so if we have e to the u, where we have some function of x as our exponent of e, then it's the same rule, just with the chain rule applied to it. So we have the derivative of e to the x is e to the x, the derivative of e to the u is that exact same e to the u times the derivative of that exponent, u prime. All right, so when we work on these derivatives, if I have e to the 3x minus 5, the derivative of that, y prime, is that same e to the 3x minus 5 times the derivative of 3x minus 5. And the derivative of that is, of course, just 3, and then 3 becomes the coefficient here, and I can write it that way. Right. If we have y equals e to the, this is a negative 1 over x squared. That's negative 1 over x squared. We have e to the negative 1 over x squared times the derivative of this. So take a moment. Finding the derivative of this is sort of a process in and of itself. And really, the way I did that was I rewrote that as negative of x to the negative 2, and then I take the derivative of that just using the power rule. So I get 2 times x to the negative 3, and then this is the derivative, and everything after this is really just a simplification of what I have here, sort of cleaning it up. So I have e to the negative 1 over x squared, moves into the denominator, become positive 1 over x squared exponent. This is x to the negative 3, sorry about that, moving that around. Bring that down into the denominator, become x to the positive 3, and the 2 remains in the numerator. All right, last one on this page. Natural log of 1 plus e to the x over 1 minus e to the x. All right. For this problem, we're going to use the properties of logarithms to simplify, or to really expand this a little bit to make it easier for us to find the derivative. So the first thing I'm going to do is split this logarithm up into 2. I have division, so it becomes subtraction. And now I'm going to take the derivative of each of these. So we're going to use some of our previous knowledge of taking the derivative of natural log. It's going to be, this is u here, so I have u prime. Derivative of this is just e to the x over the original u, 1 plus e to the x, minus derivative of this inner part here, this u, is negative e to the x over 1 minus e to the x. Everything else is really just finding a common denominator. So this is my common denominator. This needs a 1 minus e to the x factor, so I need that same factor in the numerator. This one needs a 1 plus e to the x factor, so I need that same factor in the numerator, and I distribute that through, and then I have these terms in my numerator. I can combine like terms. Notice that the minus e to the 2x plus e to the 2x cancel out, so I just have 2 times e to the 2x. So there's a lot going on in that problem. Take a few minutes, think about that, and make sure that you can perform that example, not just look at it and say, oh yeah, it makes sense, but make sure you pause the videos, or take a minute here in the videos. Make sure that you can actually create those steps on your own without looking at that before you move on from derivatives and look at the next examples, which are integration. That's definitely something, if you try that and you can't work through that, bring that to class and we'll talk about it in class.